Okay, so we are still talking about transformations of functions, so still in 2.6. Oh, let me spotlight my video, even though I think you should all be able to see me just fine. But okay, so we're still discussing 2.6, so I'll just say 2.6 continued. We've talked about 3 different types of transformations so far. We've talked about vertical shifting, so up and down shifting. We've talked about horizontal shifting, so left to right. And we've also talked about reflections around the x-axis or around the y-axis, so spinning a function around the y-axis or the x-axis. And we talked about what each of those look like algebraically. Like literally for the function, if it's f of x equals negative x squared, where the negative is depends on what kind of reflection it's going to be. And we also saw that some functions, when you reflect them around the x-axis, they don't, or rather, when you reflect them around the y-axis, they don't change. Those functions are called even. And if you take an odd function and reflect it around the y-axis, it looks exactly the same as if you reflected it around the x-axis. Okay. So now we want to move to the last type of transformation that we're going to talk about, or the last group of transformations that we're going to talk about, which is stretching and shrinking a graph. All right. So if we take a graph, or rather, if we take a function, if we multiply a number c, so some real number c, and I'm going to say the number is bigger than 1, so c bigger than 1, to the outside of a function, then what does that do? Well, consider if I had, so I'm going to finish the statement here, but I'm going to come down here and write an example. And, you know, the classic example I like to go to is a parabola because it's pretty much the easiest case to talk about. We could talk about straight lines, but you don't really like see anything happening to straight lines. So with a lot of these things, or you do, but it's harder to see. Anyway, so x squared is a great example. So I'm going to multiply some number to the outside of it. I'll just do a 2 because that's like the easiest number above 1, right? So c in this case is 2 because I'm multiplying a number to the outside of the function. So there it is, outside of the function. Then what happens, so I'm still not finishing the statement. I want to look at what happens to the graph. And if I make a real quick, excuse me, table of values, real quick, just -2 through 2, like the traditional, you know, -2 through 2 there. And I'll quickly compute these. I won't make you guys do it. So -2 squared is 4, then times another 2 is going to give me an 8. -1 squared is 1, then times the 2 is going to give me a 2. So notice I'm keeping my order of operations right here, right? Exponent, then multiply. 0 squared is 0, times 2 is still 0. 1 squared is 1, times 2 is 2. And then 2 squared is 4, times 2 is 8. Okay. Let's graph these points. So if this is 1, or -1, -2, and then 1 and 2, and of course 0 in the center. So these are the 5 x values that I wrote here. -2, -1, 0, 1, and 2. And then I need to go up to 8 to be able to graph these 5 points. So my first point is at -2 for x and all the way up at 8. I'm just going to put it there. It's pretty close. -1 for x and then 2 for y. And then, of course, the origin didn't move. Okay, so that's something to note here, that the origin of the graph did not move. Then 1, 2 is there, and then finally 2, 8. So, whoops. So we're having the same kind of symmetry like we do with a normal parabola. Oops, I missed that point. Now, to really see what's happening, to compare this to a normal parabola would be going through the points 0, 0, just like this one. It would go through the points 1, 1, and negative 1, 1, like over here. And then at 2, it would only be up at 4. So I'm just going to quickly draw a regular old parabola here. And it, oops, it would look more like this. Okay. So what's happening here? This is just one example, but I'm kind of using that to define the entire rule because it's going to work for all the functions. If we multiply a number bigger than 1 to the outside of a function, we stretch the function vertically. And it's important to say both of those words, stretch and vertically, because we're going to talk about compression vertically, and we're also going to talk about stretching compression horizontally. So we stretch the function vertically. Like literally it's like you take the legs of the parabola and are yanking them up. And to really show you this a little bit better, let me share my screen. We'll go over to Desmos and I'll graph both of these. So it'll only take a second. I'll go to Desmos. Okay, and I'll graph x squared. So there's our traditional parabola, and I'm going to color it blue because that's how I did it on the paper. And then 2x squared, which I'll color red because that's how I did it on the notes. There we go. So the red one is the 2x squared, and the blue one is like the base normal parabola that's not been shifted at all or stretched or anything. Okay, so we see that multiplying on the outside is stretching the function vertically if that number is bigger than 1. All right, so what about if the function is, or rather the number is smaller than 1? So what if I have f, and not negative, like negative is a whole different thing, right? If the number is negative, that means a reflection around the x-axis if you multiply by a negative on the outside. So notice I'm not going to be including negatives here in this discussion because we've already talked about multiplying negatives on the outside of a function. So now I'm going to say, what if you have a number that's less than 1, like a fraction, but still positive, so between 0 and 1. So let's say we have, what's the, easiest number to pick in between 0 and 1? Well, how about just 1/2? 1/2. So we have a table of values to consider here, which again, I will run through quickly. I'm going to go ahead and graph the base parabola. Oops, and I'll graph it in blue. So just the normal old parabola goes through 0, 0, goes through 1, 1, and negative 1, 1, and then 2, 4, and negative 2, 4. So that's just like that classic parabola. There we go. All right. Let's see what happens to this 1/2, or what this 1/2 on the outside does. So I'm, of course, going to pick the same 5 points for consistency here. Now, negative 2 squared is 4, and then half of that will be 2. Negative 1 squared is 1, and then half of that will be 1/2. 0 squared is 0 times 1/2 is 0, so that point stays the same. 1 squared is 1, and then half of that gives me 1/2 again. And then the final point, 2 squared is 4 times 1/2 brings it back to 2. So these points are at x equals negative 2, y equals 2, so there's that first point. Then negative 1 comma 1/2, which is like right there. So at an x value, a negative 1, and a y value between 0 and 1. And then and then the 0, 0 point is still there. And then similarly on the other side, 1 comma 1/2, and then 2 comma 2. So let's graph this. Oof. Okay, something like, oof, there we go. Something like that. All right, I'm going to write down the rule, and then we'll go look at Desmos to get a better, cleaner picture of this. If we multiply a number, now I said I didn't want to deal with negative, so how do I sandwich c between 0 and 1 to be not negative and less than 1? I say just like this. I say c literally between 0 and 1, so some fractional amount to the outside of a function. Oops, outside. We compress it vertically. So you see the red function here has been squished down. It's like you took the two legs of the parabola and instead of pulling them up like the first one did, we're pushing them down and it's becoming wider, right? It's being compressed vertically from the top, being compressed. Let's go look at Desmos real quick. So I'll keep the base parabola as blue and I'll go ahead and make this red function the 1/2, and there we go. There we see that the red function now is being compressed. It's like being squished. You can think of it as becoming wider too. That's okay. Now that's not going to translate well to other kinds of functions, but in this particular case, it's okay. You know, you can say it's becoming wider. In fact, if I start changing this, what if I made it like a 5? Then it becomes really wide. Or what if I made the, you know, the number really big in the denominator? So this number is really close to 0 now, or a lot closer. You see how much wider it becomes. Just to give you an idea here, I can do this and say, let's let n range from 0. Oh. Okay. Oh, whoops, hang on. 0 to, let's do 100 and step by. Sorry, I had to remember how this worked. Okay, there we go. So as I let this number in the denominator here get larger, this thing should get flatter and flatter and flatter, and it does. We see that here, happening here. All the way. And, you know, it's never going to be completely flat, but you can get it pretty flat if you let n be, you know, huge. Okay. So that's multiplying on the outside of a function. So I said the rule sort of verbally, well, sort of in this form here. Let me write down an algebraic rule here. So given function f of x, for c greater than 1, c times f of x results in a vertical stretch. So this is maybe like the most technical form of, vertical stretch, I suppose I could say by a factor of c. So if it's 2, then it's twice as high, right? If it's 3, then it's 3 times as high, et cetera, et cetera. Okay. And then the other rule is given f of x for c between 0 and 1, c times f of x. So both of these have c on the outside. Okay. Results in a vertical compression by a factor of c. So here's what I want you to be able to do. I want you to be able to get an example like this. And again, I'm just starting the examples over again because I don't remember what example we left off on, but okay. I want you to be able to take a function, know what its base graph looks like, and then know what each transformation on it does, and then be able to just sketch the graph. So for example, let's let f of x equal 2 times the square root of x minus 4. All right, our base graph. So what do we do here? What do we do here? I can go ahead and draw my base graph, that square root of x. I just have to know what that looks like, right? Maybe I've made some flashcards or something, and I know that it sort of looks like a sideways parabola, like half of a sideways parabola, and it starts that point that helps to move the thing around if we're going to be shifting it up, down, left, right. The point to note is that origin point at 0, 0. It's kind of where the graph starts there. Now, what have I got going on here? I've got a vertical shift. Nope, sorry, I've got a horizontal shift. I've got a horizontal shift right by 4. Got a horizontal shift right by 4 because of that minus 4 inside the function. Remember, that's from a couple days ago, or however long ago it was, when we talked about horizontal shifts. So there's a horizontal shift to the right by 4 because of the minus 4 inside of the function. And we also have a vertical stretch by 2. And that's because of that times 2 on the outside of the function. I know it's a vertical stretch because, well, that's what this rule up here tells me. All right, this rule. All right, and now I need to be able to draw this. I need to be able to take this information, all this information together, and draw the function. And I'm drawing it a bit skewed like this because I know it's shifted to the right by 4, so its little origin point needs to be right there at the point. What will that point be? That new point will be 4, 0, right? X value of 4, Y value 0, reflecting that it, or showing that it shifted right by 4. And I need to vertically stretch it by 2. So it needs to be a bit stretched up. It's like you took this graph right here and literally pulled it up by 2. So if I'm just sketching this, I don't need to like find points. I could find more points, right? I could like see what it's at x equals 5, 6, 7, 8, etc. In fact, I may want to pick like smart values that end up giving me squares under the radical. We could talk a lot about that, right? But I just want a sketch. So what I need to make sure I show is that it's not just a normal square root graph. It's been stretched by 2. So it goes a bit higher. Like a normal square root graph might just go like this. But because of that vertical stretch by 2, I'm pulling it up higher. All right. Okay. Well, I'll leave that there for a moment. Like that while I write part B, which is g of x equals, what's another one? Let's see. 1/3 x cubed. Oh, and let's make it negative. Let's say negative 1/3 x cubed. Or you may see it written as, like if you go look at the textbook or WebAssign problems, they may write this function or an example like it as negative x cubed over 3. Whenever you've got a 1 in the numerator or that fraction you're multiplying by, you can just take this part, the variable, and just stuff it up there and get rid of the 1, because the 1's not totally necessary. So this is like a more compact way of writing this. They're the same thing. Okay, so we've got two things going on here. First, though, what do? I note that x cubed is the base function. If I get rid of the divided by 3 thing and the -1, then I've got my base graph, which looks like this. And I know that sort of central point there is at the origin 0, 0, where it changes direction. That's a helpful point to note. Though in this case, I'm not shifting it. There's no addition or subtraction, either outside or inside, right? So I'm not going to be horizontally or vertically shifting it. I do have a negative, though. So I have an x-axis reflection, because it's on the outside. So recall from Friday's lecture, x-axis reflection, because of the negative sign, on the outside of the x cubed thing. And I also have a vertical compression. And now, how do I say this? A vertical compression. But the most appropriate way to say it is, I guess, by 3, because I'm like dividing the function by 3. If you said vertical compression by 1/3, I wouldn't say you're wrong either. It just depends on like what the context of your sentence is. Like, you could say the function g of x is being vertically compressed by a factor of 3. That's probably the most appropriate way to say it. But if you said the function g of x is being vertically compressed by a factor of 1/3, I would still know what you meant. Like, it's being chopped down by 3. All right. So that's a minor issue. Okay. So how do I do this? How do I show this? Does the order in which I do these transformations matter? It can. It definitely can if these things get complicated. We are not going to do that, though. The order in which I do these two operations is not going to matter. But what I do need to show is that it's reflected around the x-axis. So that means instead of being like this kind of shape, instead of going like in first quadrant and third quadrant, it needs to be in second quadrant and fourth quadrant, more like this. And it's also being vertically compressed by 3. So maybe it will help to draw the initial one with its just doing one transformation at a time. So this dotted line represents just the x-axis reflection. Okay. Now imagine this thing being vertically compressed. Now this one is being vertically compressed from both sides. So the last two examples we saw with the parabola and the square root function, they only like got vertically stretched or compressed on one side because they were only on one side. But this function does go into the negatives quite a bit, right? Infinitely so. So I'm vertically compressing from both sides, and it should look more like that on this side. So squishing that down, and like this on that side. More like that. So it's not as steep. Like it doesn't get as negative or positive. It doesn't grow as fast anymore because it's being chopped down by 3. Let me show you this function in Desmos. And get rid of all this stuff. So first of all, here's x cubed. Okay, that's the base graph. Let me zoom in. Oops, sorry. Let me zoom in a bit. There we go. Okay, now here's negative x cubed. So that just reflects it right over the x-axis. So that's like the dotted line I drew. And now I want to, there we go. And let me go ahead and put negative x cubed up here too. All right, so purple is the base graph. Then we reflect over the x-axis, giving us this red graph. And then we apply the 1/3, which squishes the graph a bit to finally end up on what I've drawn here as the black line. Now here, how about this? I'll make these all match here to what I did in the notes, just to help you make sense of it. There. So the dotted line is just the x-axis reflection, and then the solid red line is the actual vertical compression happening there. Okay. are we? Okay. So you notice I'm putting multiple transformations together now. That's kind of the point, is that you learn each one individually, and then you can go back, or you can move ahead rather, and put all these different transformations together, and the rules don't conflict with each other most of the time. Meaning that you can learn this all piece by piece and then just like stick all the pieces together. There is one case where you can get into some issues where if you are both vertically shifting and reflecting over the x-axis, there's two different, wait, is that the one I'm thinking of? Yeah, there's two different ways you can do that, and that's going to come down to like an order of operations kind of argument, but I'm not getting into any of those, and I haven't put any of those on the homework or exam. So, all right, let's talk about horizontal stretching and shrinking, and let's do that by kind of skipping the construction and jumping straight to the rules, just to save time. Okay. We're going to contrast these to the rules for vertical stretching. If we multiply a number greater than 1 to the inside of a function, we blank the function, whoops, horizontally. So for the vertical rule, it was we stretch the function, right, in the same setup. Multiply a number c greater than 1. On the outside, that's a stretch vertically. If it's inside, it's a compression. So I'll say we compress the function horizontally. So it's a bit backwards. It's a bit backwards. And then likewise, if we multiply a number between 0 and 1 to the inside of a function, and I'm going to show you examples of this. I'm skipping the like construction, you know, looking at tables of values and stuff, but I'll still obviously show you examples of these rules working. If we multiply a number between 0 and 1, so some fraction like 1/2, 1/3, or maybe 2/3 or something like that, to the inside of a function, then we stretch the function horizontally. So let's consider f of x equals, so I'm using parentheses now because I'm going to be stuffing stuff inside of the function, and I'm going to start off with just like an x squared function. But let me start with a 2x squared like this. Okay. So I've said that this should compress the function horizontally. Okay, so I'm going to say if this is a normal parabola, red dotted line here is a normal parabola, then a horizontally compressed parabola should be like skinnier and should grow faster. There it is. That's what this rule tells us. Now, that looks like a vertical stretch, though, doesn't it? That looks very much like how we described something like here with a vertical stretch, with blue being the base parabola and then the red line here. It looks like a vertical stretch, and that's no coincidence. You can actually show that if you just show that this function is the same as if you take 2x squared like this, that's just the same as like 4x squared with a 4 on the outside. So a horizontal compression, so what's the point here? On the left here is a horizontal compression, right? It's a horizontal compression by 2, but I'm just going to be vague about it and say horizontal compression. That's what that is. It's a number bigger than 1 on the inside of the function, so it's a horizontal compression, is equal to, and on the right here, I've explained the function just by distributing the square across the product there, which is legitimate. You can distribute squares across products and division, not addition and subtraction, but this is legitimate, is equal to a vertical. Well, what is it when it's a number multiplied on the outside of the function that's bigger than 1? That's a vertical stretch. So it's no coincidence that these graphs look very similar. Now, are they exactly the same as like this one back here? Is a doubling inside, squishing it by 2 inside the same as pulling it up by 2? Well, no, because, well, I'll show you why. I mean, because what ends up happening depends on the function, right? Like in this case, doubling inside actually results in quadrupling outside because of the square. So I don't want to get into like exactly how they're equal. That's why I was kind of vague here. But the point is that if you look at this and you say, wait, this horizontal compression looks exactly like a vertical stretch, then you're right. Then you're onto it, right? You're getting kind of one of the big points here. And we'll also say a similar thing about the other case. But let me write down an example for that. And then we'll go look at some pictures. So let's look at f of x equals, so the inside, I'll put a inside the function. I'm going to do, so this case, if we multiply a number inside the function that's between 0 and 1, so some smaller than 1 fraction, we stretch the function horizontally. Okay, so if I just kind of trust that rule, I know what my base parabola looks like. My base parabola it's like that, sort of. And I'm stretching it horizontally, so I should expect like this leg to be pulled out like that, and this leg to be pulled out like that. That's a horizontal stretch there. And if you say, wait, that looks just like a vertical compression, this horizontal stretch looks like a vertical compression. Again, you're onto something there. That's true. And the way I can show that is I can say, well, look at this. A 1/2 x all squared is the same as a 1/4 x squared. Right, if I distribute the square to both of these. So on the left here, I have a horizontal stretch. That's what's going, a number less than 1 inside is a horizontal stretch, is equal to a vertical compression, which, I mean, like physically that makes sense. Like imagine like a bouncy ball, right? A bouncy ball. If you squish it from on top, then it's going to get wider horizontally, right? If you squish it vertically, it's going to have to get wider horizontally. And if you take it horizontally and squish it horizontally, then it's going to have to get taller. It's going to stretch vertically. So that like natural thing that we all know just as humans, because we know how like objects move, that's working here in the analysis of these graphs. So what's the point of all that? The point of these two green statements that are the two that I wrote in green font here. It's just it's not to say that when you're doing these that you should always write this down. It's just to point out that this really is happening, so that if you are doing these problems and you notice this, that you don't think you're crazy, right? It really is happening. Now, when you are doing one of these problems and you're asked to like graph something like this, you should still, for the purpose of this problem, think of this as a horizontal stretch. okay, as a horizontal stretch. Let's do some actual examples with that. Let me see, hang on, give me 1 second. I'm just thinking because we're still in 2.6, which is fine. I mean, 2.6 is like a huge section. We could really spend like a month on 2.6. There's so much to say. So let me see. And our exam is next Wednesday. So we have 1, 2, 3 class meetings to cover 1.5, 7, and 8. I mean, 2.5, 7, and 8. Okay, I know what I'm going to do. Okay. Did I tell y'all already? If I haven't mentioned this, we're not meeting on Wednesday, the 24th. We're not meeting virtually because I have to proctor an exam for a different class, but I will still upload a video for that day. So let me write this down over here in the corner. No virtual meeting. 2/24, but there will be a video to watch. And I'll upload it in the usual location, and I'll name it, you know, like I do all the other ones. I'll call it MS112 February 24th meeting. I'll probably record it today just to get it off my plate, and then I'll upload it early for you. But we won't actually meet that day. And what I'll do, since we are falling a little bit behind for how much we need to cover before next Wednesday's exam on March 3rd is the exam, is I will probably make that video longer than just an hour. I'll try to get through all of 2.7. Okay, cool. So example 2, let's sketch a graph of each function. Let's take a cube root. We haven't dealt with one of those in a second. Let's take a cube root with and let's subtract a 1 from it. So again, I'm putting these things together, putting different transformations together. All right, base graph, cube root of x. So how do I know what the base graph is even supposed to be? Like, how do I know to write down cube root of x as my base graph? Take away all the extra operations. Take away the 1/2. Take away the -1. What are you left with? Cube root of x. What is that shape? Well, I gotta know that. Gotta know it's like a sideways cube. It's like a sideways x cubed graph. And that little spot where it changes directions is going to be right at the origin. Now, what have I got going on here? From the inside, I have a 1/2, so so I know that's horizontal, and I have to remember, is that stretch or compression? Go check my notes, and it's a horizontal compression. So horizontal compression by 2, or I could also say by 1/2, but I'll say by 2 because of the 2 in the denominator. So I'm cutting this in half. That's why I'm saying compression by 2. Okay. And I also have a vertical shift. Whoops. Vertical shift down by 1 because of the -1 on the outside of the function. Okay. So if I graph this, I know what my base graph looks like. I'm going to do the horizontal compression first. So I'm going to compress this horizontally. So I need to it's important to think about what kind of compression it is, right? Horizontal compression is coming from the sides. So that's going to take this graph, which still goes through 0, 0. And instead of it being like this kind of shape, like here, I'll draw the base graph as a dotted line here. So that's like this just cube root of x thing. It's going to be compressed. It's going to be more like this in that direction and more like this in that direction. If that doesn't make sense to you, think about that horizontal compression is the same as vertical stretching, right? Horizontal compression is the same as vertical stretching. So pulling these away from that x-axis, it's like you're lifting this line up and pulling this line down. So sometimes that idea of like thinking about these, how these horizontal and vertical stretch and compression are related to one another can help understand how this, because this is kind of hard to think about as a horizontal compression, maybe. Okay. Now, I also need to vertically shift down by 1, so I'm not done here. And actually, since I went ahead and drew that as a solid line, I should probably draw a new graph. And that's okay. You can draw you can do each one of these transformations as a whole new graph if you want. Now, when I shift this down by 1, I need to think about what's the easy point to think of, this anchor point. My anchor point is going to now be at 0, -1. If I'm shifting down by 1, that y value is changing to -1. So I'm going to now anchor this graph right there at 0, -1. And I'm going to try and draw the exact same shape I did here, just shifted down. So I'm going to draw it like that. It's as if I literally like erased the coordinate plane or just erased the x-axis and like redrew it up here, right? That's like all that should happen because this graph should maintain the exact same structure and just scoot down a little bit. Let's look at it so you believe me that it actually would look like that. So let's, oh, come on. If it's gonna let me. All right, let's get rid of all of these guys. All right, so let's just, oh gosh, I have to go to functions. These always take longer to graph because it makes you go dig all the way for a cube root shape. Okay, there's the base one, and then I'm going to draw the final product here. So we have 1/2 x and then -1 outside. Wait, oh no, did I mess up something? Oh, dang it, and it's recorded too. My mistake is recorded for posterity, how great. Okay, gotta go fix something. This, thinking about too many things at once. Okay, f of x is equal to cube root. Oh, let me go back to, no, I just realized I made a big mistake here. 1/2 x minus 1. We have a horizontal stretch, not compression, horizontal stretch by 2, or by 1/2, however you want to say. I'm going to say by 2, and also a vertical shift down by 1. Okay, so when I draw this, let me just start. I'm just redoing it because that was a big mistake and easier to just redo it. Okay, so my base graph, there it is, cube root of x, cube root of x. And then I'm going to horizontally stretch it. So it's actually, that's more like a vertical compression. So a horizontal stretch is going to have it be like this. Be like this. Okay. Horizontally stretching it. And then I'm going to shift it down. Yeah, sorry, hopefully, maybe you guys saw that mistake and were thinking I was crazy or something. I hope so. That's like a rookie mistake. Got my mind on other things. Just thinking about how to cover all this material before we have the exam. Okay, so still shifting it down by 1. That shift is right. You still shift it down and maintain that structure. So it's horizontally stretched. So that's the same as a vertical compression. So hopefully you see how that, you could argue that's definitely a vertical compression there. And then the graph should maintain the same structure as I shift it down by 1. There it is. That's the final picture there. And can see that in my graph here. It's actually hard to tell that it's been horizontally stretched because it's just the nature of this graph. It's hard to tell. So if I like took that 1/2 away inside, it's hard to tell. It's hard to tell just because of the nature of the shape of this graph, because it already grows so fast to the left and right. Okay. Oops. Okay. So this is officially the right way to do this one. All right. Let's do part B. That was still part A, so let's do another one. There are some graphs that it's hard to see that they've been vertically or horizontally stretched at all, even for large stretch or compression factors, like the rational function or the reciprocal functions like 1/x² and stuff like that. If you stretch or compress those, either way, it's like really hard to tell because they grow so fast. They, have these crazy asymptotes. So typically we don't choose those as examples to show vertical or horizontal stretch or compression. The classics are kind of the x², x³, and square root of x and cube root of x. So let me do, well, what's the only one I haven't done? I guess, I think I've done at least one of each. Let's do a g of x equals (2x³). 2x all cubed, so that 2 is on the inside. No other transformation going on here. Okay, base graph x³ with that origin point where it changes direction at 0, 0, even though that point's not going to change here because I haven't shifted it up or down or left or right. I've got a horizontal, now let me be very careful and actually think about what this is. Horizontal, what inside the function is, if it's inside the function and it's greater than 1, that is a compression. So this is a horizontal compression by 2. Okay, so I'm going to take my base graph, which I'll draw as a dotted line, as I normally do. So like that. Okay, nice cubic shape there. So this is x³, by the way, that's the base graph, right? x³. Now I'm going to horizontally compress it. Horizontally compress it, so from the left and right, and it should look more like this. Same as a vertical stretch, right? It's the same as a vertical stretch. And how can I show that, like, analytically or algebraically, I guess? How can I show that this, in fact, is the same as a vertical stretch? Well, I can say, well, check this out. 2x all cubed is the same as 8x³, right? If I cube the 2 and the x, this is what I get. So a horizontal compression by 2 is the same, for this particular case, is the same as a vertical stretch by 8. So it's quite a stretch, quite a stretch. And how these numbers are related is going to depend on the nature of the function. Okay. Alrighty, so that is, let's see, we only got 10 minutes. So 2.5 and 2.7. I think I'm just going to do another example, kind of putting all these ideas together. And I'm going to call it a new example because I'm not going to be focusing on just horizontal stretching compression here. So let's call example 3. Same instructions though. And probably only have time for one good one. So let's say sketch a graph of the function. Sketch a graph of the function f of x equals, let me go find a hard one. Let's do square root of negative 2x and then plus 3. And I'm going to get you guys involved in this one. So there it is. There's the function. I'll give you a second to think about it. It's a square root of negative 2x plus 3. All right, so Maya, what is the base function for this thing? What would the base function be?
Will it be 3?
Well, the base function should involve x, right? So when you're identifying the base function, you're taking away all the extra operations.
So it just be, hold up, let me see.
So if you took away the negative 2 and the plus 3.
It would be x?
With the square root on there.
Oh, square root, okay.
Yeah, square root of x. So taking away all the extra operations except for the defining piece of this graph, which is the square root part. That's really identifying the shape of this graph. So we have square root of x. And then let's see, Nikita, how many operations, or rather, no, how many transformations do you think we'll have on this graph from the negative 2 and the positive 3? And can you name one of them? You're still muted. You came unmuted for a second, but you're muted again.
I'm sorry, what was the question?
What can you name a transformation that would come from this function?
No, I can't.
Okay, that's okay. Makira, any idea what the negative or the 2 or the plus 3 would do?
Wouldn't you not add it, but wouldn't the negative 2 end up changing?
What would the negative 2 do?
Would the negative 2 like change to a positive maybe? If you're taking it out of the radical?
We won't take it. We're not going to take anything out of the radical. The negative 2 is going to do something, but we don't ever take these functions and like do operations with them necessarily like that. Let's see. What would the positive 3 do? Addition to the outside of the function is a vertical shift, right? Vertical shift up by 3. That's the plus 3.
Oh, that's what you meant by that. Okay.
Yeah. Okay, so any idea what the negative or the 2 would do?
Wouldn't the negative 2 make it go down to?
That would only be if we subtracted outside the function. Like if this was -3, that would be a shift down by 3. So it very much matters how the numbers are attached to the x, right? If they're attached via multiplication, like this -2 is, then that's going to be some kind of stretch or compression, and also the negative is going to be some kind of reflection. So if you have a negative inside, so the vertical shift, by the way, is coming from right here. I feel like that's obvious because it's a 3 and 3, 3, right? Now the negative in here is going to result in a y-axis reflection. So we have y-axis reflection because of the negative. So here I'll put this in parentheses, +3 for the vertical shift, minus inside the results in a y-axis reflection. And then let's see, Kimberly, what would the ×2 do inside the function?
It would do a horizontal stretch, right?
Yes, good, thank you. Horizontal stretch. Oh wait, no, compression. You made the same mistake I did a second ago. Horizontal compression, because it's opposite to the case when it's outside, right? If the number is bigger than 1 inside, ignoring the negative because we've already taken care of the negatives. Since this number is bigger than 1 inside, that results in a horizontal compression. And how do I know that? It's coming from the ×2 inside. Okay, so with all of that, I need to graph these transformations. The base graph looks like this with origin at 0, 0. Origin at 0, 0. My first transformation I'll draw, again, order can matter. Sometimes order will definitely matter, but I'm specifically picking problems where the order doesn't matter. So I can go ahead and like vertically shift it up by 3. So I have 1, 2, 3, and I'll just draw the same graph again. There it is with its new origin at 0, 3. That's coming from the vertical shift up by 3. Now I'm going to reflect it over the, reflect it over the y-axis. So you notice I'm drawing a new graph for each step. And it's still up here at 1, 2, 3, right? That's where my graph is. I'm going to reflect it over the y-axis. So, whoops, like that. And then finally, I'm going to do a horizontal compression. Oops, that's kind of ugly. All right, there we go. So it's still up here at 1, 2, 3. It's still pointing to the left because of that y-axis reflection. And now I need to compress it horizontally. So it's going to get like larger vertically. So it's going to be more like that. It looks very similar, right? Sometimes it's hard to tell the compression apart. Like this graph and this graph look similar, but if I was to superimpose this one as a dotted line, it would be more like that. So this solid red line here is the function with all the transformations put together, -2x plus 3, square root of -2x, and then a plus 3 outside. Okay, that's it for today. No time really for questions because we got like 30 seconds before class ends. So keep an eye out for that video that will be up sometime tonight or maybe tomorrow for Wednesday's lecture. Okay, see y'all later. You're good to go.